Good morning. I'm recording section 4.1 for the Math 1431 class. Okay. So this section is involved with one-to-one function and its inverse. So what we're going to do is to define a function that is one-to-one. So the definition is a function. It has to be a function is, I usually write down one-to-one like that, function, or you could spell that out. Right? If, now you know a function is for every x, there's only one y. Now we could go all the other way also. Say if for every y, there is one and only one x value. Okay? So that means for every x there's going to be one y, for every y there's going to be one x. So we add in one more condition in it, for the function to be one-to-one. Okay, what does this mean? This means that, okay, if those are the y value, okay, you have 2 points. So f of a equal f of b, and that means a gotta be equal b. Right? It cannot be something else. Right? And also, with that in mind, since your function originally satisfied the what? The vertical line test. Now we change it. Also, we add another condition in there. So for every y, there is only one x. So that means it also satisfies the horizontal line test. So that means if you draw a vertical line through your graph, it could only crosses the graph at one point. Okay? Alright? So a one-to-one function will satisfy a vertical line test. At the same time, it will also satisfy your horizontal line test. Right? So let's look. Determine if the function is one-to-one or not. So that means I'm giving you a function. So all you have to do is check for every y, there's only one x. And what do you think? And I don't think so, right here. Okay. So this y, -1, okay, is mapped into 2x value, 1, 3, 1, 4. So the answer is not one-to-one. Okay. So for every y, it's not going to be one x. In this case, it's assigned to 2x value. Right? Okay. Let's look at problem 2, and you should know what problem 2 is. Problem 2 is nothing but a straight line. Okay, a diagonal line. And every diagonal line, well, for every y, there's going to be one x, or fx is going to be one y. The answer is yes, one-to-one. Okay. Let's look at problem 3. Is this a one-to-one? That's your parent function. I'm just bringing out your parent function so you recognize it. And this is called a reciprocal function, isn't it? And keep in mind, your job is to know what those graph looks like, because you're going to need it sometime in a later chapter. Okay? And remember what the vertical reciprocal function looks like. And you have 2 branches, one on here, one is positive. So look at the horizontal line test. It satisfies the horizontal line test. So you say yes, one-to-one. Okay. All right, let's look at problem 4. And problem 4, you should also recognize the parent function. The parent function is going to be what? Square root function. And you know the square root function is going to be 3 units to the left. And you move, you move 3 units to the left, and then you stretch it by 2, so the opening is going to be like that, right? And you check with the horizontal line test. So the answer is yes, one-to-one. Okay. And find 6. We will suppose let's introduce certain graph. So I will graph 1. So you tell me. How about this one? Okay. This one is not 1-to-1 because you draw a vertical line through it. It crosses more than 1 point. Right? And you recognize it as a cubic function, I hope. And let's look at this other graph. And you're going to learn this graph later, I hope. Unless you already know what it is. Okay. This is a logarithm graph, and the answer is yes, and it's 1-to-1. Right? Okay. All right. So why do we study 1-to-1 function? Because for every 1-to-1 function, it will have an inverse function. So your job is take the 1-to-1 function and write the inverse of that particular function. And that's what our task is going to be. Okay. So let's look at f is a 1-to-1 function. All right. Then g is the inverse function of f. All right. If IFF means if and only if, the point AB lies on the graph of f, then the point BA must lie on the graph G, which is the inverse. Okay. So basically, look at what I did. You just interchange the x and y value, right? Okay. But first, we need to know the notation first. Usually, your inverse function is designated, but if f is the inverse, f is the function, and the inverse will be written as f to the -1. And that's not a mathematical notation. This is just like functional notation, stand for the inverse. Okay? The inverse notation will be this. It's not means 1 over f. So f inverse for this case does not mean 1 over f. It stands for the inverse. Right? Okay. So the idea is if A, B belong here, then B, A will belong at the inverse. Right? Okay. So actually, what we do, we interchange the x and y to find the inverse. Right? So far, so good. So what we did is we look at whether its function is 1-to-1. If the function is 1-to-1, it has an inverse. We're in the process of showing you how to find the inverse. One way of finding the inverse by the definition is we just interchange an x and y. Okay? Okay. So according to the definition, if f has an inverse, f of 3 equal -4, then what's f inverse of -4 is going to be? It's going to be what? It's going to be 3, because the point right here is what? 3, -4. So on the inverse, it's going to be -4, 3. Okay? So you just interchange an x and y. How about this one? F has an inverse, okay? And the inverse of f inverse of 6 is equal to 1/2. So what is the original function evaluate at 1/2? And that will give you 6. Right? So you can look at that. The inverse have what? X to be 6, y to be 1/2. So the original function we have x to be 1/2, y to be 6. Okay, right? Okay, so now we're ready to look at the graph. What's the relationship between the graph and its inverse? Right? Okay. So we're going to give it a graph, and your job is to graph the inverse. Right? So therefore, as you read this right, when you interchange it, that means it's reflection over the line y equal x. All the point will reflect from f to f inverse and from f inverse to f by reflecting all your point through, oh, sorry guys, to y equal x. Hey, so let's do that. Here's my graph. So I'm going to give you the graph. Let's say 1, 2, 2, 3, 4. Okay. Let me just give you this graph. Okay. That's a one-to-one function. Now, if I'm going to ask you sketch the graph of the inverse, well, all you have to do is take your points and reflect it through the line. This is the line y equal x. Okay. So this point is what? Let me write that down here. That point is 0, 4. So when you reflect it, it's going to go on 4, 0, because right there when you reflect it, which is the same thing as interchange your x and y. Right? Okay. And so that point, that thing's going to go there. So what's this point? This point is going to be 2, 0. When you reflect it, it is going to be 0, 2. Right? And any point on the reflection line will stay in the reflection line. So therefore, and that's what your graph looks like, right there. Okay. So the whole graph is reflected through there. Right? Okay. Next one. That's a half a parabola, in case you didn't know what the graph looks like. All right, let's do this one. This is one. And the one I did was the log graph. All right. Okay. And I'm going to find, okay, so this is your f. I'm going to ask you to graph f inverse. So we're going to reflect all the point through the line y equal x. So this is 1. So that gives you 0, 1, because this is 1, 0. Reflect, that would be 0, 1, right? And now, since I didn't give you any point, you're going to have to just watch this part of the graph. Well, reflected up here. So you keep on reflecting the point, and that part will be that way. Okay, I kind of drew a little wider. And was this part of the graph? Well, this part of the graph is get closer to the y-axis. And since you reflect it, interchange x and y, so this part will get closer to the x-axis. Okay, so this is your f inverse, right? F inverse x. Okay. And if this is your log graph, this is your exponential graph, right? Okay. All right. So let's look at your definition of inverse function. Right? F is a one-to-one function. G is the inverse of the function of f. Right? If provided the composite function of f and g of x turn out to be x, and also the composite function of g of f also give you x. Okay? So they would be inverse of each other. So let's find out. Okay. You're asking, is f and g inverse of each other? Well, so therefore we're going to go back to the definition. I'm going to look at f circle g of x. Okay. And Remember what that means? That is a composite function, and a composite function between two functions, it will be called f of g of x, right? And so I'm going to replace g of x, and that notation tells me to go to the f function, replace all the x for 2x minus 6. So this x right here on the f function will be replaced with 2x minus 6. So it will be 1/2 times x. That x will be replaced with 2x minus 6, and you have a plus 3. So that means, that notation to me, you go to that function, replace all the x for that value. So all you have to do is distribute, and that would be x minus 3 plus 3, and that will give you x. So going this direction is true, so I need to verify the other one. So that means you have g of circle f of x. That's a composite function again, and we would say g of f of x now. And I will replace f of x, and f of x is 1/2 x plus 3, and now you go to the g function and replace that for 1/2 x plus 3. So it'll be 2 times x here. X become 1/2 x plus 3, and you have minus 6. So therefore, you distribute a 2, you have x plus 6 minus 6, which is give you x. Okay? So you satisfy the definition. So therefore, you could conclude f and g are inverse of each other. Okay. All right, let's take time and do the next one. So let's see you know how to get started. Follow through your handout. Okay. So let's test the first one first. F circle g of x. Keep in mind your function is under this condition now, right? Okay. So that become f of g of x. Okay. And g of x is x squared minus 2. So you go to the f function and replace all the x for x squared minus 2, and you have plus 2, and that gives you square of x squared. Okay. Okay. And since all the x are going to be positive, so therefore the absolute value of x is going to be x. Right? Okay. That's the definition of square of x. Right? So that's satisfied one case. So let's go to the next one. G circle f of x equal g of f of x. And what is f of x? F of x is right here. So therefore I'm going to replace f of x for x plus 2 square root. Now this notation tells me go to the g function and replace all the x for the square root of x plus 2. So we have square root of x plus 2 squared. That means I have to square the x minus 2. And that means I have x plus 2 minus 2. That will give me x. And the answer is, therefore, f and g are inverse of each other. Okay? So far, so good. So what's that mean? That means if I ask the question is, tell me what f of f inverse of negative 2 is. Well, since the inverse of each other, they always going to come out to be x, right? Since x is negative 2, you would have negative 2. Right? Let's assume f inverse of f of 1/2. Okay? Okay, so therefore that will also give me 1/2. Right? I could use a g function. I could call g as a f inverse, right? So it will designate it. Let g be the inverse of f, then I could just say f of g of -2. It was still going to give me -2 because g is an inverse of f. All right. Oh, so we know what it is now? So let's find it. Okay. Here we go. Example. Okay. So in order to find the inverse, all right, what do they have to be? They have to be 1-to-1. If they're not 1-to-1, it doesn't have, then you have no inverse, right? Okay. So let's check problem 1. Is problem 1-to-1? So you start with a function already because it's supposed to be a function. If it's not a function, I just toss it out because f have to be a function. Okay. So that looks like a function. So therefore, I'm checking is for every y, there's only one x. So in other words, I'm checking see if the y are repeating or not. That there's no y that is repeated, right? So therefore, answer is yes. 1-to-1, right? So if it's 1-to-1, how do you find the inverse? And what do we do for the inverse? We just interchange the points. So instead of the first point will be 1, -2. Next one will be 4, 3. This would be 8, -7. And that would be 10, 0. And this one would be -1, 1. That is my inverse, right? I interchange in x, y, which is the same thing as reflecting that point through the line y equal x. Okay, next one. Think about that one and tell me yes or no, and give me a reason. Is that 1-to-1? I hope you say no. Because, let's see what's repeating here. And I have a what? One here. 2 here. I've done the line the wrong one here. 2. 2 has 2 partners, 2x value. So no, not 1-to-1. And when it's not 1-to-1, it has no inverse. Okay? So that one was easy. I don't have to do anything. And once it's not 1-to-1, I don't need to find the inverse because there isn't one. Okay. Let's look at problem 3. Oh, I'm not giving you points anymore. I'm giving you an equations. Okay? So what do you think I should do? Well, to find the inverse, what do? Do we just interchange in x and y? Yes, so let's interchange in x and y. So we have 2, the x become y, and the y become x. Okay? So we interchange the next task I want to do is once I interchange x and y, so that means the y is turned out to be my inverse now. So all I have to do is solve for y. Okay? So let's do that. So you have 2y equal 3x plus 12. So I added 3x to both sides. And then I'm going to divide both sides by 2. So it'll be 3x plus 12 divided by 2. So you don't have to separate them, but I like to separate them so you can see them. And that would be plus 6. And I'm going to replace the y for the inverse notation. It'll be 3 plus 6. Okay? So the inverse of this line will be this line. It would be nice if you have time, you graph this line, you graph that line, and you will realize that all the points are reflected through the line y equal x. Okay, let's look at this one. This would look like parabola, isn't it? Open downward. Is it parabola open downward? A 1-to-1. Vertex at 6 and open that way. This is be what? 0, 6 at the vertex. Open down. The reason open down is because A is negative. And it looks like it's not 1 to 1, right? Because it doesn't satisfy the horizontal line test. Imply no inverse. Okay. So far, so good. The rest of them you just practice in finding the inverse. Right? So we're going to, what's the first thing we do? Read there, interchange in x and y. So this is y, that become x. The x become y plus 5. Okay. And the next task is what? Solve for y. Okay, let's solve for y. To solve for y, I need to isolate the what? The radical term. This is called a radical term because it's a radical equation. Okay, so let's subtract 5 on both sides. Before I do anything, I need to divide both sides by 2, so I could have this radical all by itself. So x minus 5 divided by 2, that will equal y minus 4 raised to the third power. Okay. Now, if this is a radical equation, how do you solve a radical equation? You isolate the radical, okay, and do whatever necessary to eliminate the radical. And this is radical is going to be q root. If it's q root, you're going to have to raise to the third power. You take that, raise to the third power, and that will give you y minus 4. And you're going to have to do the same thing on this side. Since you raise to the third power, you're going to have to raise that to the third power. You don't have to simplify that. Just leave it in that form. If you want to, you could take the constant. That would be 8. You could take the 8 out. But I usually leave it in that form. You add 4. And that means you just solve for y. Okay? So interchange in x and y, and then you solve for y. At the end, you're going to replace the y for the inverse notation. And that's what we're going to do. And that is the inverse of your original function. Right? Okay? Or, you prefer, you could take the constant out, x minus 5 to the third power. And don't forget, 2 to the third is 8. But you don't have to simplify x minus 5 to the third. That would be very tedious work. Right? And that would be acceptable. You don't want to do anything, you can leave it that way. Right? Okay, now fraction. I know you guys don't like fractions, but we're going to have to work with the fraction anyway. Okay? So let's look at that one. What's the first thing we do? We're going to interchange what? The x and y. 2y plus 5. After that, then you're going to have to solve for y. Well, this is a fractional equation now. So you want to eliminate a fraction. This was a radical equation, so you notice we keep referring to different types of equations so you recall what you're supposed to do. So we're going to clear the fraction by multiply both sides by LCD. You know, then you have an equation with no fraction, remember? Then we're going to distribute 2xy plus 5x equal 1 minus 3y. And this turned out to be, you have y term in this side and y term in this side. Okay? Since you're solving for y, that means it looks like y is a linear part. So you want to get all the y term to one side. So to do that, you do what? You're going to subtract, let's do it the other way here. That would be, unless you want negative, well, let's subtract 5x on both sides. Let's subtract, and then add 3y to both sides, right? So we're going to have 2x, y, I'm going to add 3y, and I'm going to subtract 5x on both sides. There you go. Or you could do the other way around, it's up to you, but either way it's fine. Right? Now how are you going to solve for y? Well, it means you have a y on both terms. This is solving for y. You need to factor out the y. plus 3 equal 1 minus 5x. To solve for y, you have to divide. This is called a coefficient of y. So you're going to divide that. 1 minus 5x over 2x plus 3. And that is your inverse. So you just put your inverse notation over 2x plus 3. Okay? All right? So let's summarize what we just did so you follow the procedure. Okay. Okay, the first thing we did was look at how can we determine a function is one-to-one or not by looking at the definition. If a function is one-to-one, and for every y, there's only one x. Okay, and that means your function will satisfy your graph, or your function will satisfy the horizontal line test. Right? So we'll practice a little bit. So make sure you know. Right? Okay. So in this case, a one-to-one function do have an inverse. So to get the inverse, we just interchange in x and y. Right? And after that, then you look at say, hey, what's that mean by interchange in x and y? Well, when you interchange in x and y, which is nothing but all the points on your original function will be reflected through the line y equal x, that will give you the inverse graph or inverse function. Right? Same thing over here, reflection, 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 right? And the line is y equal x, so make sure that's a reflection line. Okay, and then we'll go ahead and look at the definition of inverse. How can you verify what I give you on two equations, they're inverse of each other or not? The only way they could be is when you do the composite function and they come out to be x. If they don't come out to be x, then they're not inverse of each other, right? And then finally, we went ahead and we did what? We're going to find the inverse of a given function. If your given function is order pairs, so we just interchange in x and y, right? But make sure you double check as one-to-one or not. You notice in here it's not one-to-one, we just say no inverse. Okay, what happened when we give you an equation? If I give you an equation, right? If I tell you to find the inverse, you just have to interchange in x and y, and then solve for y in all those. This one I didn't have to do that because you already know a parabola could never be a one-to-one. That would save me a lot of time, or save you a lot of time. If you know that, right? Make a comment and say, hey, a parabola does not satisfy the horizontal line test, so therefore it's not one-to-one. Okay, and that wraps up section 4.1. If you have questions after you just look through the video and do the problems, you still have questions, you should email me, and so we could go through them again and make sure you understand the problem. So now we're going to go to section 4.2. So I hope I could get all chapter 4 done today. And probably that's the part. I hope by that time when we finish this, we could get back to class. I'm still trying to see if I could work with the Blackboard and do conference up. I don't know. We'll see. Okay, so here you go. Okay, so here your section 4.2, and the topic on 4.2 is called exponential function. Right? So far, in the previous chapter, you study your polynomial function. Okay? What is the difference between a polynomial function and an exponential function? A polynomial function, you look at it, your base is a variable, and your power is a numerical value. Okay? Okay. Now, when you're dealing with exponential function, your base is a numerical value, and your exponent is a variable. Right? Okay? So we just you need to understand, do I have a polynomial or do I have a exponential function? Right. So we're going to, maybe some of you, this is the first time, it shouldn't be the first time you look at an exponential function, but we're going to graph them anyway. So let's see. The best way to graph them, if you don't know, is to pick points. Right? So we will pick some point. I think that thing doesn't dark enough, so I'm going to use this one. Right, so therefore, let's pick some point. Obviously, when you graph, you're going to pick 0, you're going to pick some positive number or negative number. So we're going to pick 0. 2 to the 0 power, everybody should know is 1. So we'll pick 1, that will give me 2. 2, that will give me 4. I could continue, but I think you already know, see the pattern. When I pick 3, it will be A, so therefore it's increased very rapidly. Right? So let's pick -1, and that will be what? 2 to the -1 will be 1/2, right? How about -2? 2 to the -2, 1 over 2 squared, which is 1/4. Right? So let's plot them and talk about the characteristic of your exponential function. All functions of this kind will have this point in common. I don't care what the base is. I mean, the base, you can't have a negative base. The base got to be positive, right? Okay. And you would say when x equals 1, y is 2. When x equals 2, y is 4. And they increase very rapidly. 3 would be 8. So in that portion, when I increase the x value, it's not a straight line. It's going to be a curve in that form. Right? Right. So let's look at the other side. And now the other side gets smaller and smaller. So when you get -1, it could be -1/2, and -2 would be -1/4, and that one. And it will never cross the x-axis because there's no y that will make x equal 0. Right? Okay. And that's what we mean by exponential function. And for this one, I chose b to be 2, so therefore you have a base that is greater than 1. Okay. So that would be one class of exponential function where your base is greater than 1. So let's look at your other class. The one I'm picking is right here. Right? And your base, it turned out to be from 0 to 1. Right? Okay? And you notice x cannot be 1. When x is 1, it's just nothing but horizontal line. Right? Okay. So that's why base has got to be greater than 0. And right? In this case, beta greater than what? Greater than 0 here. So we don't say that one got to be greater than 0. Right? Okay? 2 is greater than 0. Okay. All right. So let's pick point again. So let's pick 0. Again, you have 1. And you pick 1, that would be 1/3. Pick 2, that would be 1/9. Now this portion will go totally opposite what we just got. In here, when I increase the x value, your y value increase very rapidly. So what happens if I increase the x value to the positive, and your y value getting smaller and smaller and smaller? But they still have 0, 1 in the problem. So when x is 1, you have 1/3. When x is 2, you have 1/9. So that part is going to be, again, it never crosses. So in this case, when you increase the x value, what you have is the y value gets smaller, smaller, and smaller. Let's go to the negative. -1. 1/30 to -1 is going to be 3, right? -2 is going to be 9. So on this side, it's going to go up big. Okay, so yeah. Oh, dusty over again. You have, look at this one you have, right? You have 2 classes right here. One class of exponential function is going to be greater than 0. The other one will be between 0 and 1, because you cannot have a base to be negative number, because that doesn't make sense when you raise it to a power. What when you raise it to 1/2 power? That would be imaginary when you're negative, right? So the restriction is right there. So that will break it down into two groups. The base greater than 0, the base to be between 0 and 1. Okay. So when your base is all greater than 0, this is what the graph looks like. And when all your base is between 0 and 1, right, 0.3, between 0 and 1, 9, 10, 1/2, whatever, it's going to be, all your graph is going to look like this, right? So there's only two graphs for your exponential function. Is your base greater than 0, then it's going to be going very rapidly. If you have your bases between 0 and 1, then it's going to be decreasing, okay? And you should also know that this turns out to be what? In application, this is your exponential growth, this is your exponential decay, right? Isn't how you like this? Is your growth, exponential, and this would be what? Exponential decay. Okay, so those are the two groups when you do application. Okay. So this is called, I'll give it a name now. The definition of exponential function is y equal b to x, where b is greater than 0, okay, and b does not equal to 1, and she forgot to type b lie between 0 and 1, right? Let's see what the b is. B is okay. Oh, okay. Well, actually, b is greater than 0. It will cover that part anyways. I don't need to put it down. All right. So when b is greater than 0, divide it into two groups. One group is bigger than 1, and the other group would be lie between 0 and 1. Right? Okay. And that is 1 supposed to be. I was right the first time. And this is called an exponential function. Okay. And now you could look at both graphs and could state the domain and range. And you notice you could use any x you want. That means your power could be choosing whatever x you want. So that means your domain is going to be from positive infinity to negative infinity. And look at the graph. Okay? Your exponential function is never going to be, the value is never going to be negative, right? Because look at the graph, it never go below the x-axis. So the y value is always positive, and since it doesn't cross the x-axis, could never be 0 either. So you have an open interval from 0 to positive infinity, right? Okay. So the next task is we'll look at how we graph, right? So let me just draw something in here. So you are doing it on your own, so make sure you draw your axis here. Okay. Now, what's the parent function? Your parent function would be y equal 4 to the x power. So we're doing transformation. So y to the base is greater than 1, so therefore I have to use my parent function right there. Remember how we did that? We put that in dotted. And what transformation did we do? It's going to be what? It's going to be down 2, right? So what it says? You move down 2, right? So that's 4. Since I have a horizontal asymptote line, so I need to take care of that first. So I move the horizontal asymptote line down. I'm going to do it in red so you can see. All right, and then move my reference point, because every exponential function of this kind will have this point in common. So I move down 1, 2, and that point will be right there. And the shape of the graph is the same. So since I didn't stretch it, so that is my graph. Right? And you notice since you move down, and your range will change, right? Okay, so your domain will stay the same. So your domain will be negative infinity to positive infinity, and your range, and since you move down the graph, originally it's from 0 to infinity. Now since you move down 2, so it will be from negative 2 to positive infinity. So from negative 2 to positive infinity, right? Make sense? All right, let's look at this one. So I'm going to draw my grid. Okay. And look at your base. Your base is between 0 and 1. Okay? So when your base is between 0 and 1, your parent function is this form. And let's look at your transformation. That means you're going to move the graph 3 units to the right. Okay? And then you're going to do what? You're going to move up 4. Okay? So your parent function would be y equal 1/2 x. Your transformation would be right 3 and then up 4. Okay. Remember, we always follow through the order operations. So let's look at the decay graph. That's how because this is, since the base is between 0 and 1, and your decay graph would be this form. So let's move it. Right? So I'm going to move it 3 units to the right. So it'll be 1, 2, 3. So that point is going to be right here. Okay. And I'm going to sketch that. And then that is your graph. Right? And then now I'm going to do my final graph. It means up 4. And since I do have a horizontal asymptotic line, I can move that because your graph can never go beyond that line. Right? So I'm going to move up 4. So I'm going to move the horizontal asymptotic line 4. It will be 1, 2, 3, 4. Right? So that's my horizontal. Yes. And then I'm going to move my reference point up 4. 1, 2, 3, 4. That point will be right there. Right? And then the same graph, right? I'm sorry, it's over here. I'm moving this graph, not that one. So that point would be 1, 2, 3, 4. So the graph would be in this form, okay? And this portion would be, that is your red graph, okay? Okay, so what's the domain? Domain, again, is all real because you didn't move. When your domain is all real, I don't care where you go, it's going to be all real. All right, the range, since you're moving up the graph, right? So that changes your range. The original range was from 0 to infinity. Since you move up, it's going to be from 4 to infinity because it never could, your graph can never go below y equal 4. Okay. Okay. All right. So the next thing we want to look at is, because you've been studying logarithm before, I think, and you probably have questions. Hey, what is e? Well, e has a numerical value, except you want to know, hey, how did they get that numerical value, right? So the definition of e would be, say, as x get larger and larger, right? Then what happened to your function? It has a function value, right? The function of 1 plus 1 over x raised to the x power will become e. I don't want you. Okay? Now, this is what I want you to try, since I didn't have my calculator here. You're going to try this with your calculator. You're going to pick some x value, And you notice the x value can be very large. So look at it. So let's start with what, 10,000. So you're going to replace x with 10,000 and enter. You will get 2.7 something. And then you're going to use what, 100,000. That means I'm increasing the x value. Replace that with 100,000 and punch it in, and you will get also 3.718. And then now I'm increasing the x value. Okay? The larger the x value, the closer we get to the numerical value of e. Okay? And that's how they got it. But the definition is right there. Okay. All right. So you know what e is now. So we're going to sketch the graph. Since e is approximately 2.718, and then what you want to do is look at the base and understand the transformation. The e is going to be greater than 1. Okay? And let's look at, you're going to have your parent function would be y equal e to the x power. And let's follow the order operation. That means you go to the right 3, and then you reflect about the x-axis, and at the end you always do plus or minus last, guys, or else you won't get a graph or you do reflection. Then you're going to move up 2. Okay, so let's follow that particular transformation. I got more room here, so I put it right here. Okay, since my parent function have the base to be greater than 1, so therefore I'm using the exponential graph, which is this one right here, on top right here, this one, for the base greater than 1, right? Okay, so let's follow through the transformation. Move that right 3 just like we did up there. It'd be 1, 2, 3, so that point would be right there. Okay, so my transformation would be move the whole graph dotted to the right, so therefore I have to the right 3. Okay, and I'm going to do the reflection. So when I do the reflection, that means what? That means all the positive x value become negative. So this is right here. So when I do the reflection, that point is going to be right here. Right? Okay. Is that right? Now come on, I'm asking you, is that right? And you should be correcting me already because I did that on purpose. I said, well, hell, if the base is greater than 1, why am I using your decay graph to graph? Right? I should be using this one. I should be using that one. So I hope when you're in my class, you could say, hey, we shouldn't do that. We choose the wrong graph to do my reflection and so forth, right? So instead of doing this one, I should be using the exponential graph. So my parent function would be this one. Okay? Because the base e is 2.7 something. So I'm going to move a 3 unit to the right, and I would get a similar graph. Then I will do my reflection, and this one would be down here, and that part will be over there, that part would be right there. Okay, so this is the reflection. So this will be y equal opposite of e to the x plus x minus 3. Now my final graph is I take that graph and I'm going to move it up, right? Move it up what? 2 units. Well, since I have a horizontal asymptote line, so I need to move that up 2 units first. So there'll be 1, 2. So I'm going to draw my line. And I'm going to move that reference point up to 1, 2. That reference is going to be right here. Right? I'm going to put an X in so you don't. And then this portion will be moved up, and that one right there. So the red graph is my final graph. Okay. All right. So you got to understand which graph you're going to do to transformation. So I'll do this so it calls for your attention. So you use the wrong graph, then you're going to have the wrong problem. Okay. All right, we're done with the graphing. Right. Since exponential, I like to review some exponential property with you first before I would go into solving exponential equations. Right. Here's your property. Okay. When do we add exponent? When do we subtract the exponent? When we multiply the exponent? Those are the basically three basic ones. And the negative exponents are here, and b to the 0 is 1, just like we use the point graph. Right? So take time and understand, or refresh your memory on the law of exponents. Okay, since I'm multiplying, so that means 6, well, 2 times 6 is a numerical value. And since I'm going to multiply x to the negative 5 times x to the third, that means I'm going to add the exponent. That gives me x to the negative 2. And I'm multiply y times y to the 4. That would be I add the exponent would be y to the 5th. Okay. Many times they wouldn't want you to write your answer with a negative exponent, so therefore you have to go to your definition negative exponent and convert it into positive exponential form. So your final answer will be 6 times y to the 5th divided by x squared. Right? Okay, let's look at 2. 2, I'm dividing power to the same base, and here's your property. So when you divide power to the same base, you're going to keep the same base, and you're going to subtract the exponent. That means you're going to take x minus 3, and you're going to subtract x minus 1. You notice I put parentheses in there. So keep in mind that when you subtract, you always have to change the sign when it's a polynomial. Okay, so the sign here is going to change. So you would say this is going to be minus x plus 1. Yes, so that will give you the negative 2. And what is 4 to the negative 2 by the definition negative exponent? Means 1 over 4 squared, that will give you 1 over 16. I think I wrote too big over here. Alright, so let's look at problem 3. Problem 3, you have a power raised to another power, and that's your property, so you have to do that first. So when I do that, that will give me 8. I'm raising 2 to the third power. I'm going to have to raise that to the third power. So that means I'm going to multiply the exponent. That would be 6x minus 3 for that one. Okay? I'm going to divide it by 4 to the e of what? 4x minus 3. So what do we do when we divide? Well, 8 divided by 4 is a numerical value, which is 2. Now if I divide power to the same base, I will basically subtract the exponent again, minus 4x minus 3. So you simplify that, okay? Okay. So 6x minus 4x is going to give you 2x. And this become a plus 3, right? So you have a negative 3 added to plus negative will give you 0. So that's what you're going to get right here. Okay, now let's see if you know how to multiply this kind of problem. Square. Many times I still have some of you tell me a plus b squared equals a squared plus b squared. You got to get rid of that concept, right? When you square binomial, you're going to get a trinomial. So when you square this, 2x. And this is going to be what? What's the middle term going to be? I didn't hear anything, so it'll be minus 2, I assume. And it could be plus and a negative 2x, yes? Well, you would say no. Well, then we're just going to have to multiply them out. E to the x minus e to the minus x times e to the x minus e to the minus x. So your first times the first would be e to x times e to x. That means you add the exponent. Okay. And your outer term, this is your outer term now. That's when you distribute this. And that will give you what? This times this would be minus e to the 0 power because you add the exponent. And your inner term would be also minus e to the 0 power. And your last times last would be plus e, you add would be negative 2x. And that's what we got right here, right? Okay? And this one you just have to distribute. Negative times it would be plus 2e to the, and you take e to x times e to the minus x. You add the exponent, it will give you 2 to the 0 power, right? Okay. And this is positive 2. So you have a positive 2 minus that will give you 0 here. So you have e to 2x plus e to minus 2x, right? And many times they will prefer you write it without the exponent, negative exponent. So all you have to do is write that at 1 over e to 2x. And then you want to find LCD and make it one single fraction. You cannot multiply both sides by LCD because there's no equations. There's no left side or no, right? You only have one side. So you have to maintain there is a denominator. The denominator e to 2x. So if this is over 1, well, you want that to be e to 2x. You have to multiply this by e to 2x times e to 2x. That will give you e to the what? 4x plus 1. There you go. And that would be 5. Okay? So we just rehash a little bit on your law of exponents, how to work with it. Okay? So don't lose all your skills. Alright, so now we're ready for solve exponential equation with, I even bolded it for you, darkened it, same base, same bases. Okay? And there's a theorem or property, whatever you call them. If two sides of the equation have the same base, okay? So b to x equal b to y. So all you have to do is set the x and y equal to each other, okay? Because they have to be true. If they're equal, your x and y have to be equal to each other if they have the same base. So that's exactly what you use to solve the problem. You want to convert the left side and the right side having the same base. Now don't be too fancy. The base you want to use is 2, 3, 4, 5, ... You don't want to use any fractional base unless it's obvious. They will tell you, but no, you always want to use an integer base right there, okay? So let's look at 4 as a base and a as a base. I could convert that into base 2, so therefore the base will be the same. So what is 4? 4 is 2 squared. And then you still have to raise that to the x power. And what is 8? 8 is 2 to the third, right? Yes? So you notice I'm replacing that back for that number, right? And this would be x plus 2. So your problem is 2 to 2x equal 2 to the 3 times x plus 2. Now, by the theorem or property right here, they have the same base. So all this imply, all you have to do is set the exponent equal and solve. 2x equal 3 times x plus 2. And you will solve that, right? So 2x equal 3x plus 6. So you subtract 2x and subtract 6. So therefore, x equal negative 6. All right? Okay. We started with an easy one so you can see a little better. You got to convert it in the same base if possible. If not, then we're in trouble right now because we haven't done logarithm yet. Okay, so the base I want you to use is 2, 3, 4, 5, integer base. Now, don't tell me your base is 1/9 or 1/3. Okay, so you want to convert that to a base 3. So 1/9 can be written as 3 to the negative 2 power. So I'm using 3 as a base, right? And 27 is 3 to the 3rd power, so I'm using 3 as a base. And that also is a 1 minus 2x power. And since I'm have a power raised to another power, so we have negative 2 times 2x minus 3 for that one. 3 times 3 raised to 1 minus 2x power. And then you would say the base are the same, so all we have to do is set the exponent equal to each other and solve, right? So let's do that. Negative 2 times 2x minus 3, that got to be equal to 3 times 1 minus 2x. And then you can solve that. So let's quickly solve it. Negative 4x plus 6 equals 3 minus, 6x? And let's add 6x to both sides, then you have 2x. Subtract 6 from both sides, you have a negative 3. And you'll divide both sides by 2. So the x you're looking for is negative 3/2. Okay. So basically, if I replace x with negative 3/2, calculate, and the left side and the right side will have identical values, right? Okay. The b is not supposed to be here. Knock that out. That's problem C. Okay. So what base should I use? Well, obviously, look at that. I got to use base, what, 5? Yes? So because I could write square root of 5, it's the same thing as 5 to the 1/2 power. So that raised to the 2x minus 10. And what about 1 over 125? That is 5 to what power? 5 to the negative 3, right? And that will be raised to the 5 plus x power. So what you have is 5 raised to 1/2 times 2x minus 10. And this one would be 5 raised to the negative 3 times 5 plus x. Okay. Now you set the exponent equal because the base are equal, are the same. Okay. So that's important. You want to convert the base to be the same, then you can apply your theorem above into the problem. So I just have to set the exponent equal right now by according to that theorem, and then I'm just going to have to solve it. Okay. Distribute your 1/2, that would be x minus 5. Distribute your negative 3, that would be negative 15 minus 3x. So you're going to add 3x to both sides, that will give you 4x. Then you're going to subtract 5 on both sides, that will give you add 5 to both sides, then that will give you negative 10. Right? Divide both sides by 4, and you could reduce that one, I assume. That will give you what? Negative 5/2, and that would be your x value. Okay? So that's how you solve basically exponential equation. Okay. All right. So we're going to look at some application. Well, the next question you would say, well, what happened I cannot convert in the same base? Well, if you cannot convert in the same base, you cannot apply their properties. Okay? So eventually you're going to have to do what? You're going to have to understand this other technique, and that's where your logarithm comes in. Right? Okay. All right. So we're done with that. So let's go to a little application, and you probably like this part. Now we're going to look at compound interest. Before we were looking at what? Simple interest. I equal PRT. And then you just say principal times the rate times the time. So now we're going to look at what we call compound interest, which means you get interest with your interest. In here you don't. You just multiply your principal times the rate times your 2 year. You multiply by 2. It's 3 year. You multiply by 3. Okay. So in other words, you accumulate your principal plus your interest, and then next year you use that as your principal, and you calculate it how much money you get. And that's why you want your investment to grow exponentially, which is involved with compound interest. Okay? Okay. So let's start. So I'm going to derive the formula for you so you know. Okay? So let's assume your annual rate is R. Okay? That's the decimal. You're going to convert the R to decimal, and T representing the year. So at the first year, you would take what? Your principal plus your interest. Your interest will always going to be PRT right now first. PRT, right? That's at the end of the first year. That's how much money you have in the bank. That's the annual interest rate. So what you want to do is, let's factor out the P. So that would be 1 plus, right, R, and T is 1 just because it's annually. So I could replace T for 1. And that's how much I have at the end of 1 year. Okay, I just replaced T for 1, so that's why your T is not there. All right, the second year. Well, the second year, I'm going to take this as my principal. That's how much money I have at the bank. All right? And I will get interest for that. So to get the interest, that means you're going to add the principal times the rate times the time. In this case, I'm going to put T to be 1. So you will know I replaced T for 1 already. Okay. And what do I have? I have that in common. So that means I'm going to factor that out. If I factor that out, the first term have a 1 left, and this one have R, because R times 1 is, right? And since this is at the same base, when I multiply them, so that means at the end of the second year, that's how much money I have in the bank. So you get interest over your interest, right? Next year, the third year. All right, so this become my principal now. At the end of the third year, you're going to get interest with this principal. So that means you're going to take the principal, multiply by the rate, and multiply by the time, which is 1. And since you have that in common, so I'm going to factor that out. And if I factor that out from the first term, I get 1. Factor that out from the second term, I would have R. And that implies I have 1 plus R to the third. Okay? Now, what happened if I just continue on my process into the end of T number of years? Right? So basically, my formula for compound interest would be P times 1 plus R raised to the T power, because your exponent turned out to be your how many years you have, right? Okay. And we call this basically a amount. Okay. Now that's an annual rate. Annually, you get interest through 1 year, through year. So many times the company usually doesn't, your bank doesn't say, okay, you get an annual interest rate. Usually, hey, you compound it different time, different years. How many times? Could be quarterly, could be yearly. This is yearly, quarterly, or biannually, and so forth. So let's look at what happened when you're going to compound your interest rate, right, into n times. Okay. So if I compound it n times, so that means your original interest rate had to be divided by n. And that's how you get your formula for p plus 1 times 1 plus r over n raised to the n times t power. Right? Don't forget that part. Every time it compounded in that particular period, then that will be raised to the n period, and then depending how many years, then you get to raise it to the t years, right? Okay. And now we're going to, what happened? I just do it continuously, right? And that would be this formula. Well, where's that formula come from? How come E is in there? And then you would say, right? So let me just do the substitution here, so you can see. So originally you had A equal P times 1 plus R to the n raised to the nt, right? Okay. Now we're asking the question: as as n get larger and larger, that means how many times do I compound it? So that means what happened when I compound it daily, or monthly, and so forth. So I'm getting n to be getting larger and larger. Okay, what does it come out with? Right? So I'm going to say P. I'm going to break it up so you can see 1 plus r to the n, put that in parentheses, raised to the n power t. Okay. This is the same thing as that. So as n get larger and larger, this, and look at your definition of E, this will get you P to E to the R power, this part right here, and then you're going to raise to the T, so that will give you P times E to the RT power, right? So that's where E come into your compound interest problem. As n get larger and larger and larger, you compound it indefinitely. So that's why in this become your E value. I just show you where that come from. That come from the definition of E. Right? Okay. All right. So the rest is just practicing using the formula. So here's your variable. A is how much money you have in an account, and sometimes it's called a future value. And P is the principal, and the principal is called the present value, how much money you have right now, right? How much money you're going to deposit right now. That's why they call it. And R is the rate compounded n times a year, right? And it will be n times a year, right? And T is what? The number of years you're going to leave your money in the bank. So if you're dealing with time and you don't want to touch that, you want to, as a compound it all the time till you get to 65, then you will get tremendously large sum of money. Okay, let's set it up first. The rest is the calculated activity. Once you know how to set it up, monthlies. So therefore you have A equal, how much money do I have in the beginning? Principal is what? 2,000 times, okay, 1 plus, what's my rate? I need to change the decimal point, 0.035, and how many times do I compound it? Compound it monthly, so that would be 12, right? And if that's 12, this has to be raised to 12 power. That's for 1 year. How many years do I leave the money in? It told me 3 years. So I have to multiply that by 3 here, up here, as an exponent. Okay. Now you should take your calculator. I don't know what type. Usually it's a TI 8384. You could punch it in. Learn how to use your own calculator. Okay. So you should try it. And then I'm going to put the answer down. When I punch it in, I will get 221. 2,221 and 8 cents. You always round it off to the nearest cents. Okay. Next one, I'm going to let you take a little time and set them up for me. It's going to be 2,000. What's n? Semi-annually. And semi-annually is going to be 2, right? And so therefore you have to raise that to the 2 power. And since you kept it for 3 years, so you have to, your exponent has to be multiplied by 3. So you just have to punch it in. Okay? And that should give you, what's that going to give you? Okay, I'm waiting for you to take time and punch it in. So if you match with the answer, if it doesn't, you could always correct me, guys. Teacher make mistake also, remember? And that's what I get, $2,219.40. Okay. It makes sense because you compound it monthly, so you get a little bit more money than you compound it semi-annually, right? Okay, quarterly. What's quarterly means? Quarterly means what? How many times? How about 4? Is that right? So with n is 4, so you're going to have to raise it to the 4 power here. Okay? So that's within a year now, compounded. Now you want to leave it in 3 years, so you're going to have to raise it to the 3rd power. So you multiply that by 3. Okay. And take some time and learn how to use your calculator. Punch it in. And you should have, because some of you are pretty expert on your calculator, $2,220.41. Okay? So that makes sense because this is more than that one, and it's smaller than that one because that one compounded monthly. Okay, next one, daily. All right, we don't talk about leap year, so therefore we're going to use, what we're going to use? How many days are there in a year? 365. So you're going to have to raise that to 365 power, since you have it down in there for 3 years. So you have to raise the exponent to the 3rd power also. Okay. Now this I'm just follow through the formula, and you punch it in, and you will get again $2,221.41. Right? Okay. It's not that much different between compounded monthly and daily, right? Okay. And you would imagine when you do compounded continuously, that would be e to the RT, and R is what? Oh, let's put 2,000 first. And R is 0.035, and then you're going to multiply that. I'm going to put that in as a multiply by 3 as an exponent. You should, everybody should know what the E button is. If you don't, you better practice finding the E button. Equal. Okay. And punch it in. And what do we have? Not that much more. I hope not. This would be $2,221.42. Okay. This is only a little bit more than when you compound it yearly, daily here. So that's the application of your exponential function. Okay. All right, let's rehash again, so make sure you grasp the concept before I go to the next section. Okay. There are 2 types of exponential graph. Right? The growth graph and exponential growth, exponential decay. On your exponential growth, your base is going to be greater than 1, while your decay one, your base is lie between 0 and 1. Right? Okay. And you need to understand that the domain and range are the same no matter whether you have exponential growth, exponential decay. Right? Look at the graph, you will realize that your range is always above the x-axis, so that's why your range is from 0 to positive infinity. Right? And then again, we'll review a little bit on transformation. Okay. So we use transformation to graph, so you don't have to punch in all the points, punch in. You can use graphing calculator, so make sure you understand your transformation involved. Right? Okay, so you should practice a little bit on your own, because I assigned some transformation problem where you have to practice. And then we went into how do we solve exponential equation. This is what we call exponential equation. Okay. So the theorem tells you that if they are the same base, you got to convert it in the same base. Then you set the exponent equal to each other and you solve. And keep in mind, this is the kind of base you're going to use. Don't try to use fractions, okay? Because you try to convert it in fraction, that doesn't make sense sometimes. Okay, right? So use your base to be 2, 3, 4, 5, 6, 7, 8, 9, whatever. You notice I did that. I convert 4 and 8 to base 2. I convert 1, 9 to 27 to base 3. And this one to base 5. Okay? And then we look at application. And the application is what we call compound interest. Right? You get interest over your interest continuously and so forth. And this other formula you need to remember. Right there. It will not given to you, so you got to remember that. That's why I take time to derive that for you. So you know that's only compounded annually. So when you compound n times a year, you have to take the rate divided by n. If you take the rate divided by n, you have to raise it to n power. And since you leave the money up in t here, that's why you have to multiply that by t as an exponent. And in here, continuously, I'll show you where the e come from the definition of e right here, when you break that up. And it turned out to be p e to rt. People like to say that this is perk. I don't know, so that's how you memorize it. All right, and then you need to understand monthly, semi-annually, quarterly, daily, and continuously, right? So all you have to do is practice a little bit. There's some application problem in your homework, so you practice. Okay. So we're good, I hope. All right, let's go to the next section. How's that? And what is the next section? Now we're going to go into logarithms. What do you think? Oh no, we're not done yet. We need word problem. You remember? Oh, I didn't turn the page. There we go. Oh, let's do that. Okay. We need to have word problems. As you know, you can't get away with word problem, no matter what it is. So let's turn the page and turn to the next page and invalid word problem. Okay. So the idea is you need to know what formula to use and what are you looking for, right? If you are using A equal P, times 1 plus R to the n power raised to the nt. You notice how many variables you have? 1, 2, 3, 4, 5. You have 5 variables. If the problem given to you with 4 information, then you could solve for the 5th variable, right? You have to know 4 things to solve for your 5th one. Okay, so let's read the problem so you know. Okay, what are we looking for? So you need to read the problem and understand what is given here. Okay, so A is given, and at the rate of R is given, I'm going to change it to 0.08. Right? And the bond can redeem for 10 years. All right, so in this case, T is equal to 10. All right, and what else do I know? I need to know N, do I? Do I know N? Yes. Do I compound the what? compound it right here. Oh, good. So that means n equal 12. Okay, so what variable is missing? The p. So basically you're solving, you're finding p. So you know 4 things, and you could always solve for the 5th variable, right? So you just replace 1,000 for a times a equal p times 1 plus r is 0.08, divided by n is 12, raised to the nt, so 12 times 10. Okay. So once you set it up in this kind of problem, you don't have to do step by step. You could just go to your calculator. Okay. So since I'm solving for p, basically whatever that is, you just divide by that number, right? Okay, so therefore I'm just right. Now make sure you don't truncate it too early. You want to let it go since you have a calculator, and you only round it at the end. Or if you're going to be in trouble when you go to population or money-wise, then you truncate it too early, your answer will not match. So you take 1,000, divide by this number, whatever that number is, 0.0812, and I'm going to multiply that out for you, 120, that's easy. And then you punch it in. If you don't like, if this bother you, you could rewrite that. You say, or you could punch this in, raised to the 1 plus 0.08 and the negative 120. Right? That means you just bring it on top. And your final answer is whatever you have to put in right now to redeem a 10-year for $1,000, you have to put in $450.52. Okay? With your calculator, you punch it in either one. All right, next one. Now, next one, we're going to find the interest rate now. Well, obviously, interest rates are needed for $1,000 to double in 5 years when it's compounded quarterly, right? So what's that mean? You know your P is $1,000, right? And compounded quarterly means 1 plus r divided by 4, since you know what r is, raised to the 4 times what year? 5 years, so times 5, right? And to double, that means I should end up with $2,000, right? Okay. So you're solving for r, right? You know, in this kind of problem, when they say double, basically that can divide out. You could set up the equation as 2 equal 1 plus r over 4, and this would be raised to the 20th power when you multiply 4 times 5. Okay. All right. Now, how are you going to solve for r? Well, obviously, this looks like you need to get rid of 20. To get rid of 20 power, you would take the what? 120 roots on both sides, don't you? Yes? So you would say 2 to the 1 over 20 power. That means when you raise that to the 1 over 20 power, the 20 will cancel out and leave you 1 plus r over 4. And you're solving for r, all right? So wait till at the end before you round out, guys, or you're going to come out with something different. So you're going to subtract 1. And that will give you r over 4. And you're going to multiply both sides by 4. So it'll be 4 times 2 to the 1 over 20 minus 1. That's what you punch in at last. And then you round off your answer. You start rounding it too early, and they will, and then you're going to use a different value to calculate. Right? It's always nice to round your answer up to at the end. Okay. And the decimal value is going to be what? I think it's 0.1410. So that would be what? 14, approximately 14%. So interest rate got to be 14%. Okay. Let's look at problem 4. Okay, you want it to be what? You want it to be double again. And this time you're going to compound it continuously. Except you're looking for the time. Okay. So you have $5,000 and continues to e to the RT, so it'd be 0.065 times t, and you want to double it, it's going to be 10,000. So actually, when they say double, you could ignore your principal because eventually you're going to divide that. They're always going to give you 2. If you say triple, there's going to be 3, and you don't have to worry about the principal, right? 0.065 t, right? So what should we do? Now, here's what the problem is. You have never solved an equation for the exponent before, right? Well, unless they're the same base, then you could do that, but they're not the same base, right? So what are you going to do? For some of you should already know, but for those who's still a little rusty, so we can't do that till we go to the Logarithm chapter, Logarithm section. We'll come back to that problem when I will just say, let's refer to that problem, see how we solve that problem, right? So keep in mind, this kind of problem, when you're solving for the variable, I say unknown, and they're not the same base, you're going to apply your logarithm property to that, right? So we will go back to that problem later when we finish the law section. All right. Hey, I almost forgot those word problems. That's important. Okay. So let's go to logarithms today, guys. So we did exponential, and let's go to logarithms. How's that? All right. So let's do that. I'm lumping. I have to lump section 4.3, 4.5, 4.4, 4.5 together, right? Because they're kind of smoothly. If I lump it together instead of breaking it down. Right? So when you do your homework or when you look at a problem, when you finish this section, you should maintain what you know to apply those different sections. Okay. So your 4.3, 4.5 basically is just how do we use logarithm to evaluate things. Right? Okay. All right. Since for some of you maybe this is the first time, so therefore we're going to look at the graph first. I'm asking you look at the graph of y equal 3 to the x power. All right. So we did what? Didn't we do 2 to the x power already? So again, x equals 0, y equal 1, 1, this would be 3, that would be 9, this would be negative 1 would be 1/3, negative 2 would be 2/3, would be 1/9, right? Okay. And what kind of graph do we call this? There's a name for that. What is it? That is going to be your exponential growth graph, right? Yes? If you plot those points, you will get an exponential growth graph because the base is bigger than 1. All right, now I'm going to try something with you. We're going to interchange an x and y. Oh, that sounds familiar. What do we do when we interchange an x and y? That means we're looking for what? For the inverse, right? Okay. So let's do that. If I'm going to take this and interchange an x and y, so that means this is 1, that would be 0. This is 3, that would be 1. This would be 9, that would be 2. That would be 1/3, that would be negative 1. This would be 1/9, that would be negative 2. Okay? Okay. So basically we're looking for the inverse function. Okay, and remember we did that back in the section 4.1, alright, when we interchange an x and y. Alright, so rather than plot the point, I also want to review with you, or why don't we just reflect it through the line y equal x, because that's inverse, with all the point will be reflection, right? Okay, so this point would be right here when I reflect, right? And then that portion would be here, and that portion would come down here. Okay, so you notice we have y equal 3 to the x power, and when we interchange an xy, the red graph become x equal 3 to the y power, so all the y become x, all the x become y. Right? You can't graph that unless you solve for y. So in order to do that, I have to introduce a new function. Right? This is true if IFF means if and only if, that means go both ways. Y equals the law of x to the base 3. Okay. And from that, you can see that logarithm is nothing but exponents. Okay. This is a law, and the law is the exponent of your exponential function. So now you know the exponential graph and the logarithmic graph are inverse of each other, right? Okay. All right, so let's fill in the gap here. Is this a function? The answer is yes. Okay. What is the relationship between the function and the original graph? And I already told you what they are. They are inverse of each other. Inverse function. I should put function there, but okay. What is the name of this function? And I already told you. It's a logarithmic function. I put function in here. Okay. And if you look at your calculator, you only have 2 buttons to dealing with log function. One of them is log, right? Okay. Definition logarithm. So this is what it is, guys. This is your whole definition. So that means your exponent is going to be your base b. So since there is your exponent, so it's going to be the exponents of your exponential function, and the base is obviously what base you're dealing with. The base is b, and what's the remaining x. Right? That's how you convert back and forth. Right? Okay. So when you have a base 10, this is what we call common law. Common logarithm. Right? And in your calculator, you know that they don't put 10 as a base. Right? So they will save their money a little bit and say have a little 10 script here. So when you look at that problem on your calculator, you're dealing with base 10. Right? So according to the definition, that means your base is 10, and this is your exponent equal x. That's how I convert back and forth. Right? And you have another button, and you notice your other button is going to be ln button. Okay? And when you're dealing with your base to be e, this is called your natural law. Natural logarithm. That's when your base is e. But when your base is e, instead of say log base e, it's basically they use ln. Right? So this represented, so law of base e can be written as ln. So anytime you see look at ln, that means you're dealing with base. Right? So to convert it back and forth, since logarithms are what? Exponent, so your base is e to the y power will give you x. Okay? So you have this, you convert in that form, then we'll go in that way. Okay, let's look at the graph. And I already did one graph for you already. Okay, the first graph is when your base is greater than 1. It's similar to your exponential, and it's going to be like this. And that's what we did, the red graph right here. This is your parent function, whatever that is. Right? I don't care what base is, as long as the base is bigger than 1. This is what your graph looks like. Instead of having horizontal asymptote line, like you have in an exponential graph, now since you interchange in x and y, you will have a vertical asymptote line. And you know that you cannot take a law of a negative number. X is always positive, and you cannot take a law of 0 either. Okay? If you type that in your calculator, they will say error. Okay? They will say domain error because you're making a domain problem. Okay. All right, let's do what happened when your graph is having the base. Okay, instead for me to graph it so you memorize it, so I'm going to do is to look at the reflection, right, on your decay graph. Right. This is your decay graph, and since your law is what? Reflection to the line y equal x, so I will graph that graph for you. This point will be right here, okay? And this portion right here, that portion, will be down here when you reflect. So going to go this way. And where's this portion go? Well, obviously because this portion of the graph on your exponential graph is what? Get closer to the x-axis. And since you interchange x and y, so when you reflect it, it will get closer to the y-axis. Okay, the red graph is your log graph. So this one is the y equal log x to the base b, while your b is between 0 and 1. This graph is when your b is greater than 1. Okay? Either one. You're going to have domain to be x is going to be greater than 0, which is the range of your exponential graph, right? And the range, it could be all real. An even notation, or I should put it in interval notation form. So it could be negative infinity to positive infinity. And for that, it would be what, from 0 to infinity, right? Okay. And there is a vertical asymptote line now. In this case, the vertical asymptote line is x equals 0, which is the y-axis. Right? While your other one, exponential, you have a horizontal. Okay? So your logarithm graph will have a vertical asymptote line, okay, because you interchange in x and y. Okay, so let's start graphing. Okay. This is up to, so therefore, in case you didn't know that, I could rewrite it so you could see it. 1/2 power, that's my base, plus to that is the same, right? So let's look and see what graph am I using. There's only two graphs, just like exponential. Exponential graph, you have two graphs. One is greater than 1, the other one between 0 and 1. So your logarithm graph, it's going to be one is greater than 1, the other one's between 0 and 1, right? And since your base is 1/2, so this is the parent function you're going to use to move your graph, right? So I will graph that one and dot it. Okay, since I'm going to move up to, Here's my scale here. So that point will be 2. Okay. And I will sketch the graph. And this dot line will be my, I should do it in red here, but that's what I did. Okay? We just move up 2. That's all I said. And you notice the domain and range did not change. You know, the domain is going to be 0 to positive infinitive, and the range is from negative infinity to positive infinity. Okay. It doesn't change the range when you move your graph from up and down. But when you move it from left and right, it will change your graph domain because you have an asymptote line there. Moving left and right means you have to move the vertical asymptote line. All right, so let's look at this one. Let's look at the transformation. My parent function is y equal ln x. So that means left 2 and then reflect x-axis. Okay, so let's do it over here. I'm going to have more room here, guys. So let me just do it like this. Okay, which graph am I going to use? Well, ln x means your base is e, right? And e is bigger than 1, isn't it? So basically you are using this graph. That's your parent function. Okay? Now I'm going to move left 2, so that means this way. Now since I have a vertical asymptote, so I need to move the vertical asymptote 2 to the left also. Okay, and then I'm going to move this point 1, 2 right there. Okay, and then that will give me similar graph. So when you shift it right and left and up and down, the shape of the graph stay the same. The only time changes when you stretch the graph or compress the graph. Okay, now I'm going to do my last one. The last one I'm going to do it in red, so therefore you know it's my final graph. It reflects over the x-axis, so anything on the x-axis will stay on the x-axis. So when I reflect it, anything involved with a positive, this portion will become the negative portion of the graph. That is negative, and when I reflect it, that will be the positive. You notice it can never cross the vertical asymptote line. That's why you have it. Right? So the red graph is this graph right here. Okay. And so we could write down the domain. If you move it left and right, your domain changes because your domain is bigger than 0. So when you move it to the left, so the domain is going to be x is going to be what? Greater than -2. So it'll be -2, comma 0. Right? And what is your range? Your range is all real. That means we could cover all the y values. All right. Let's see if I need to. Oh, I'm good. All right. Question. All right. So let's do the go to. Right. Practice a little bit. So you need to be able to convert back and forth. That is part of the requirement. When you do logarithm, you got to convert from log to exponential, from exponential to log. And that's why I wrote a definition out here, right? Okay. So I'm going to do the first one again. When you take from logarithm into exponential form, so you need to start with your base. So your base is 3, and logarithms are exponents, so this is going to be your exponent, equal 81. Makes sense, right? Okay. Let's do from exponential to log. Right? So when you do from exponential to log, you need to understand what base you're dealing with, since you're dealing with base e. So therefore, it would be ln, right, of 2 and equal, since logarithm exponent, we go to exponent. And this is your exponent, right? So your logarithm is the exponent of exponential. And ln, because I'm using ln because the base is e. Which is the same thing as the log to the base e of 2 equal x, but we don't use the log to the base e that way. We're required to write it as ln. Okay, let's take time and see if you grasp the concept, going from exponential to log, from log to exponential form. Okay. See, I'm stopping so you could let you concentrate a little bit, and well, of course I'm going to put it down, but when you do it, you should just cover up and go from there. Okay. So let's see if you grasp it now. When you're changing from logarithms to exponential, and you start with your base, and since ln have base e, right, and since logarithms are exponents, so in here this become your exponents and equal the number x, right? And let's do it other way. Okay, if I convert from exponential to log, okay, what do I start first? Obviously you start with the log, right? And since the base is what? 4 of the number 0.125, and that will give you the exponents of negative 1/2. Okay? So far so good? Let's do this one. When you convert logarithm to exponential form, you start with your base, and your base is 10. You notice that's how it works. They don't put 10 in there. Okay? To what power? Well, logarithms are exponents, so the power should be negative 2. That's what that is. So negative 2 is the exponent of this, and that's equal 0.01. Okay. And in here, when you convert exponential form to log form, you will start with the log to what base? In this case, the base is e. So rather than write lg to the base e, you write ln, okay, of the number 0.5, and that should give you the exponents x plus 1. There you go. Okay. So you don't have to solve for x. You're just converting right now, so therefore that's all you have to do. Okay. The next task is see if you remember how to find the inverse function. Okay. And you notice the inverse function, the logarithms and the exponential are inverse function. Okay, so let's go through the procedure again so you recall. We're going to interchange in x and y. Okay. Now to solve for y, I need to convert it into exponential form. Okay. So the base is 2. And to the x power equal y, and that is your inverse. Okay, they're inverse of each other. Okay, I'm going to let you do that one a little bit, see how you turn out. So I interchange in x and y. So we have x equal 2 to the y minus 5, right? And then we're going to do what? We're going to solve for y. Well, to solve for y, we need to make sure that is you're by itself, so you need to add 5 to both sides. Okay. All right. And then what? And then we would convert it into logarithm, right? And since the base is e, so you would say ln ln of what? I'm glad you think about it a little bit. Okay? So that means ln of x minus 5 is equal to the exponent. Yes? And then to find the y, you just divide by 2. So it would be 1/2 of ln of x minus 5. That will give you e, that will give you y. And that would be your what? That will be your inverse function. Yeah. Equal f inverse of x. Okay. So changing from logarithm to find the inverse will be exponential form. And in here you have an exponential form. To find the inverse will be logarithm. Right? Okay. All right. Now let's practice on evaluating. Okay. Okay. So that allows you to convert back and forth. There's no calculator for this part, so make sure you know how to do it. It's easy, just punch in a calculator, whether you understand the concept or not. The idea is that we want you to understand the concept. Okay? So this one you could be able to do in your head. Okay? So basically, I'm asking, I could put question mark in here. Oh, I could put a variable in here. Why don't I just put a variable in here? Let's call this A. How's that? Okay. So you're looking for A, whatever that is when you simplify it. So since you have what? Logarithm, and you want to change it, you always want to change it to exponential form. The base is 10 to the A power equal 1,000. If you're still having trouble seeing it, you could convert that into the same base. So this would be 10 to the A equal 10 to the third, right? Yes? And then since the base is the same, then you say, hey, this gives you A equal 3. But most of the time you could see that problem, hey, the answer is 3. Right? Because 10 to the third power equal 1,000. Let's look at this one. And let's also call that A. Okay, so you say 4 to the A power equal 256. Can I convert 256 to base 4? And you should tell me the answer is, or you can convert into base 2 if you want to. Okay? So why don't we do convert into the lowest base? And 4 is 2 square to the A power. And this is 2, I think it's to the 8 power, give you 256. Okay. So therefore this implies 2A equal 8. So A should give you 4. That means if I take 4 to the 4th power, I would get 256. Okay. All right, let's look at the next one. Let's go to problem 3. Problem 3 says, let's call this A again. So when you evaluate logarithm, you need to convert it into exponential form and then answer the questions. So that means my base is what, 1/2 raised to the A power, give you 32. Is that right? Logarithms are, so you get 1/2 times 5. So again, I'm going to have to convert it into the same base, right? So that become what? 2 to the negative 1 power And 32 is what? 2 to the 5th? So that means minus a equal 5, so a equal negative 5. That's easy. Okay, last one on evaluating. Now this is very similar to that, so you should know what the answer is for that one. Okay. Does everybody know the answer? So let's call this a again. So you say 1 over 8,000 raised to a power, right? Is that right? Come on, answer me. Yeah, you should say no, because the base is 10, isn't it? So you should write that as 10 to the a power equal 1 over 8,000. Yeah, sometimes I just purposely make mistakes, so see if you're thinking. All right, so in here I could change everything to 10, base 10. So 10 to the a power, this is nothing but 10 to the negative 3, right? Just like we did before. Except in this case, imply a is equal to negative 3. Okay? So evaluating is a logarithm is easy if you convert it back into exponential form. In this particular case, you could always convert it in the same base. If you're not in the same base, you're going to be in trouble because you haven't looked at logarithm, solving different kind of problem yet. All right, so let's look at solving now. Okay. So to solve a logarithmic function, you always convert, if you have lost something, you convert it in exponential form. Exactly what we did up here. So that's why I put that problem up here, right? So let's convert it into exponential form. So the base is 3 to the 4th power will be equal x. So there's nothing to do in that problem except evaluate 3 to the 4, and you should know it's 81. Okay, let's go to problem 2. Hey, that one might be a little hard. You take the base, raise to the 2/3 power, equal 4. All right, now this is a different kind of equation solving now. I put those in there so it's just refresh your memory how to solve it. This is what we call exponential. This is what we call what? Radical equation problem, right? So you isolate the radical. This is the radical terms. And then you ask yourself, what power do I need to raise to eliminate the 2/3 power? So what power should we raise to both sides? So I could get b to the 1st power. And I hope everybody say the reciprocal of the exponent. So you raise it to the what, 3/2? So that means you're going to raise 4 to the 3/2. Right? And that side will give you b. How about this one? We take the square root of 4, right? The square root of 4 is 2. And 2 to the 3rd, 2 to the 3rd is 8. Okay. So we could continue till you grasp the concept here. Learn how to solve your simple logarithmic function. So this would be 16 to the y power equal 8. So how will you solve this one? You would say, well, it looks pretty simple. I could convert it all in the same base. Okay? And it looks like the base is 2. So 2 to the what power? 2 to the 4th power is 16. And 8 is 2 to the 3rd power. So this implies 4y equals 3. So y equals 3/4. Okay, things getting easier now? It make more sense? Okay. All right. Now, all those are logarithm now. Okay, what happens if I give you an exponential form problem? So when you have an exponential form problem, you're going to convert it into logarithms, right? So it's because your x is a power, right? So let's convert that. So according to your definition, this would be e is your base, which is ln now. So you say ln of 3 got to be equal to your exponent, 2x minus 1. Okay. And then you solve for x, so you add what? You add 1, so usually I put it over here so you don't get confused. You might think that 3 is add 1. So you're going to add 1 to both sides, and then divide both sides by 2. Then you will have 1 plus ln of 3 over 2 equal x. Okay. So the idea is when you have logarithm as an equation, you want to convert it into exponential form, and from exponential form you can solve. Right? If you're given an exponential form, you could convert it into logarithm if you're solving for the variable as an exponent. Okay? And then that's why you convert it into logarithm form. Okay, let's look at this one. So what form do I convert it in? This is a logarithm. So I need to convert it into exponential form. And ln is base e. And logarithms are exponents, so therefore this would be your exponent equal to the number x plus 3. To find out what x is, you just subtract 3 from both sides. You notice that we did not punch in anything, so you got to be able to solve that algebraically. I assume you know how to use a calculator, so, but you got to learn your math first before we use the calculator. So you make more sense that way. If you keep on using a calculator, you lose, even though you don't understand. You say, I got the right answer. Well, answer doesn't mean anything. You got to know what you're doing. Okay. So we got that question. I hope not. I hope you understand. So if you don't, look at your videos again and pick the part that you don't understand, then you start emailing me so we could go through them again. All right? Okay. Next. Now, since we're dealing with logarithms, and logarithms have certain properties, so that's what we're going to do. Look at the properties of logarithm. All right? Okay. And then we will solve the equation with more than one logarithm. Right? Okay, here we go. Since logarithms are exponents, so what do you do when you multiply power to the exponent with the same base? So you're just going to add the exponents, right? So that's why you have we call this the product properties. Yeah, that doesn't work. That means the law of x times y become the law of x plus the law of y. Okay. So if I have the law of 2 times 3, that becomes the law of 2 plus the law of 3. Actually, it doesn't have to base 10. It could be any base, so I'm just going to put a b in there, right? Not any base, any positive base. Okay? And then we have a quotient property. There's your quotient property. When you divide x by y, and since when you divide power to the same base, you subtract the exponent. That's why you have the law of x to the base b minus the law of y to the base b. Okay. Okay, you have a power property. So, and the power property say, what happened? You have a power raised to another power already, base b. So you have x here, this is power, and you're going to raise it to the r power. Okay. And since you're multiplying, so that means this property, your r could come out. So that's r times law of x to the base b. That means you take the product. This is exponent, that's an exponent, so you multiply. Just like you have 2 to the 3rd raised to the 4th power, it should be 2 to the 3 times 4. Okay, those are the most important ones. And the rest is just like large common sense. Okay. So let me ask you, the log to the base b of 1, what's that going to be equal to? That means I'm asking b to what power give you 1? Isn't what I'm asking you? Then you would say, obviously it would be 0, isn't it? B to the 0 power equal 1. And the next one, the law of the law of b to the base b, and what's it going to equal to? Well, I'm asking you, say, b to what power would give you b, so obviously it's to the first power. Okay. Okay, in this one, if you have a base, you raise to the power log. Right? What's that going to give you? And you notice those two matches, and that will give you x. Okay, there's only 1, 2, 3, 4, 5, 6. One more properties. Okay, the last property is what we call the change base property. So I'm going to write that down. Okay, that's because if you're going to do anything with the calculator only has 2 buttons for logarithm, base 10 and base e. What happened when I say, what is the law of phi to the base 2 or base 3? Well, base 3 is not in your calculator as a button, so you punch. If I say, what is the law of 6 to the base 10? You can, no problem, you can punch it in, because you do have a base 10 button in there. Okay? So, but you don't have a base 3 button, you don't have base 2, and so forth. So that's why you could do that with the change base property, right? So if I were asking you, find that when the base is not 10, when the base is not e. When the base is 10, you just punch it in, LOG button. When the base is e, you just punch it in, you just use the LN button. Okay? So if b is other than that, so you're going to have to change it. So you could do what? You could use the base 10 and you could use the base e to find your answers. So let's assume I'm using a base 10. So therefore, that will give me LOG of x. Now divided by LOG of b. Okay. All right. So let me take an example problem here, or let's say, you could also use the ln button, so it'd be ln x divided by ln b. Okay. All right. So we could punch this in very easily. So let's assume I ask, what is the law of phi to the base 3? Well, you don't have base 3 button in your calculator with your logarithm, so that's why you could do this. So you either convert it into base 10 or convert it into base e, and they come out an identical answer. So let me say LG phi divided by LG 3. And you should punch it in, and that will be the same answer as you use ln phi divided by ln 3. Right? There's also come out with, so they come out with the same answer, except you're using different base to get that answer. This uses the base 10, base e. I change it to base 10 because I have that button in the calculator. I change it to base e because I have that button in the calculator. And I think I did punch it in approximately, unless I copy wrong, 650. There you go. Try it and see if it works. Right? Okay. Now, since most of you are going to take calc, so you're going to have to get used to the ln properties. Right? So instead of using law base, I'm going to rewrite all the property using ln. All right? So you get used to it. So this one will be ln x times y, that become ln x plus ln y. How's that? This one is going to be ln x over y. Whoops, sorry guys. That will become ln x minus ln y. Okay? So this has any base. I'm just using base E to rewrite the problem, because you're going to, if you're going to take calculus, you're going to see the ln all the time. Okay? And this one, you have ln x raised to the r power. That means you can take the r out, would be ln x. Okay? And the rest is evaluating. You're going to use ln evaluation all the time. So when you ln1 is going to give you 0. ln e is going to give you 1. Right? And the change base, oh, this would be e to the ln x equal x. That's this property right here. Right? And the change base property is understood right there. Right? I could use the ln to change base. Okay, your job is to be able to use the property, either expand them out. This is called, when you go that way, you call expand. When you go the other way, you call condense. And condense into one single logarithm. And they will say expand it using more than one logarithm. Right? Okay, so let's look at this one. Use the logarithms to expand. I mean, you're going to rewrite it with more than one logarithm according to the properties. So you look at here, you have a product. So according to your product properties, so that would be the law of 3 x squared plus the law of y to the base 3. So that means x squared times y, the law of that becomes the sum of this law. Right? Now you want to simplify with your power property. So that means you're going to rewrite that as 2, take the 2 out, the law of x to the base 3 plus the law of y to the base 3. Okay. All right. Next one. This one right here. You have a quotient and you also have a product. So therefore we do the quotient. You always do the quotient because you have a numerator and denominator. So it'd be ln of 3y to the third minus ln, I'm going to rewrite this as x to the 1/2 power. That's what square root is, right? Okay. Now you have a product right here, so you have to apply the product property. That become ln3 plus ln y to the third minus that. Make sense? You don't want to do it all one, because your property only dealing with two items. So you're going to deal with the quotient with 2 items, then you're going to deal with the product with 2 items. All right? And then now you're going to apply your power property to simplify. ln3 plus, take the 3 out here, with ln 3 times ln y, and this would be the 1/2 comes out as a ln and x. So that's what we mean by expanding. You write the original problem, you are in condensed form using more than one logarithm. So, okay. Let's look at the next one. So the next one is much easier. You rewrite it as the law of ab squared raised to the 1/3 power. And by your law of exponents, you can say this is the law of a to the 1/3 times b to the 2/3. Okay. You don't have to do it. You can take the 3 out first and apply it, but whatever your preference is going to be. Now I have a product, so I'm using the product properties. The law of a to the 1/3 plus the law of b to the 2/3. Then you apply the what? The power property. Your power comes out. That would be 1/2. The law of, 1/3. The law of a, that would be plus 2/3. The law of b. Okay? So that's going logarithm into expander form. Now I'm going to give you the expander form. and I'm going to ask you to do what? Condense it into one single logarithm, right? Right there. Write it using one single logarithm. Okay. All right. This looks like you have a, now to do that, you're going to have to work the reverse process. In here, you notice you apply the power property last. Now, when you have it in that form, you're going to have to do the power property first. So that becomes the law x to the third plus the law of y to the third power base 3. Now you have the law of something plus the law of something. That means it's turned out to be a product. That means x times y to the third with the base 3. Okay? Okay, let's continue. Now, remember what you're supposed to do? You're supposed to take, when you condense it into one single logarithm, you need to work with the power property first. So that would be ln a to the 1/2 minus ln b squared plus ln c. Now, since you're probably only dealing with 2 items, so therefore you're going to have to work with just 2 items in the beginning, and then work with, after you've done that, then work with the other items, right? So this means it's a quotient, because you ln something minus ln something, or you have it up here. Okay. So let's do that. That means ln of a to the 1/2 divided by b squared. And so now I'm going to take care of the L and C now. Okay. Oh, that's a plus. I'm sorry, plus sign. I didn't see that. Right? So you had this law of something plus the law of something that turned out to be the product. So it'll be a to the 1/2 divided by b squared times c. Okay. And if you want to, you could change that to ln square root of a times c divided by b squared, because 1/2 power is square root of a. Right? Okay. Now let's do something with the numbers, right? I don't have any power, so therefore I'm done with that. So let's do that first, because your law property only dealing with two law value here, okay? So that means you have a product right here. So that means the law of 2 to the 12 times 10. And you're going to subtract the law of 15 to the base 2. So now you have a law of something, subtract the law of something, and that will give you, well, you notice I didn't multiply that out yet. Okay, I'm going to wait till at the end. Maybe I could just reduce rather than waste my time, say 120, and that doesn't make a difference. Right? So this would be the law to the base 2, and it would be 12 times 10 divided by 15. Okay. Or you prefer to do 120 divided by 15, I don't care. So let's simplify that. Phi going this 3 times, phi going that 2 times, and 3 going to 3 1, 3 going to 12 4 times. So eventually you have this, and eventually you could simplify that into 2 to the what power give you 8. I hope you will say 3, and the answer is 3. Okay. Next part, guys. Next part is solving logarithm equations. You have a theorem, just like you did with exponential form. If the law of something equal law of something, the same base, so this got to be equal to each other, and that's what you do. Okay. Okay. So the first example problem is matching with that one. You have the law of something equal the law of something, and you have the same base. So those two going to be equal to each other. So I would say x squared minus 2x got to be equal to 3x minus 6. Now it looks like quadratic. Whoa. So what am I going to do? I'm going to set one side equals 0. Subtract that. That would give me minus 5x. And S6 equals 0. And then you're going to factor, right? Okay, I keep adding